This video about the physics of an accelerometer. Einstein would have been greatly assisted with an accelerometer, but he didn't have one. You, on the other hand, almost certainly have one in your pocket or in your bag. Your phone needs to know when you tilt between portrait to landscape and back again. So there's an accelerometer on board. This app shows the effect of gravity on tilt. Zero tilt, maximum tilt, zero tilt. So how would Einstein have been assisted with an iPhone? Well, the first thing he may have done is simply drop it, since he was greatly interested in free fall. Suddenly, a thought struck me, recalled Einstein. A man falling freely would not feel his weight. This led Einstein to a much deeper question. Posed in a modern sense, it runs something like this. You're looking at the accelerometer on your iPhone when suddenly you drop it. One of two things can happen. Number one, nothing. The blue line keeps bumbling along at negative 9.8 meters per second, meaning that gravity pervades all of space. Number two, something. The blue line jumps to zero, meaning that gravity doesn't pervade all of space. Okay, so it's number two. Gravity doesn't pervade all of space. To examine the physics of the situation further, it's instructive to pull the iPhone to pieces and examine the accelerometer in detail. The first thing to notice when opening the iPhone is that the contents are almost all battery. The logic board takes up nearly all of the remaining space, and the accelerometer is on the back of that. You can see that it is very tiny, measuring only 3 millimeters by 3 millimeters. Looking at the rear view of the iPhone, the accelerometer is in the top left-hand corner. Turning it over and using the geometrical centre as the Cartesian origin, the accelerometer is 22 millimeters across and 32 millimeters up. The data sheet for this particular accelerometer states that it's a MEMS device, micro electromechanical system. In short, there are extremely tiny mechanical bits moving within the 3 millimeter case. The block diagram shows that the input to the device is acceleration that feeds the X, Y and Z vector inputs. In this case, we'll examine the Y input. The moving bit is a piece of metal that is really the bottom plate of capacitor 1, C1, and the top plate of capacitor 2, C2, joined together. As the iPhone tilts, the metal moves. When the metal approaches the top plate, the capacitance of C1 is increased, and as it falls to the bottom plate, the capacitance of C2 is increased. The change in capacitance is processed by the multiplexer. The output is a charge that is an analogue of tilt. This is shown here on the accelerometer app. Whatever way the iPhone is turned, the mass on the piece of spring wire falls in the downwards direction. The most straightforward method of constructing an accelerometer is to use a proof mass suspended on the end of a piece of spring wire. This is an analogue of the tiny piece of silicon suspended within an accelerometer integrated circuit. This box is a film studio with an accelerometer on board. A GoPro camera is fitted into the box and the proof mass is suspended in front of this scale. The whole assembly looks like this. Three, two, one. When the accelerometer drops, the proof mass floats weightless. Einstein concluded from this that gravity can be made to disappear in a free-falling reference frame such as this box.
Okay, right now, Houston, the voltage is looking good. And we had a pretty large bang associated with the caution and warning there. And as I recall, B was the one that had a amp spike on it once before. Roger, Fred. In the interim here, we're starting to go ahead, but
There's a significant question about Einstein's reference frame here. Why the astronaut and shuttle weightless? We could simply conclude, of course they are. They're in space. But let's take a moment to think further. The shuttle is a maximum of only 620 kilometres high. The radius of the Earth is 6,371 kilometres, and the shuttle is 620 kilometres above that. Using Newton's law of universal gravitation, we can find the gravitational force in each case, the shuttle on Earth and the shuttle in space. This shows the gravitation in the shuttle is 83% of that on Earth. This means that neither the astronaut nor the shuttle is free from gravitational attraction, not by a long shot. So why are they floating about? The answer is that they're in free fall, just like the proof mass in the yellow box. Unless an intervention takes place, they'll be in free fall for eons.
Houston, we've had a problem.
The reason for this is that the shuttle is moving at an extremely high velocity in the orbit around the Earth. For every 8 kilometres travelled along the equator, we drop 5 metres. For an object to drop 5 metres, it takes 1 second. So if we're travelling at 8 kilometres a second, we'll drop at exactly the same rate as the Earth falls away beneath us. Watch this segment carefully and you'll see that as the spacecraft falls, its velocity is just enough to ensure that the Earth falls away by the same amount underneath it. The fact that gravity can be made to vanish within a free-falling reference frame, such as a spacecraft, leads to this question. Is there a difference between gravity and acceleration? We commonly use the expressions F is equal to mg and F is equal to ma as meaning the acceleration due to gravity and proper acceleration are the same. Einstein came to the conclusion that they're equivalent. This means that if you imagine you're in space, floating weightless in a room, and you suddenly drop to the floor, there's no experiment that you can do from within that room to determine whether someone's parked an Earth-sized planet under the floor, or if you're being accelerated upwards by a rocket at 9.8 metres per second. Gravity and acceleration are equivalent, but is one posing as the other? The equivalence of gravity and acceleration are the second and third things Einstein might have checked with an iPhone. Laid flat, the iPhone will register 0g in the y direction. Acceleration in either the negative or positive y direction will cause registration on the screen. The inertia of the proof mass will bend the tiny spring within the accelerometer IC as a force is applied to it. This force will be the same for both gravity and acceleration. We can check this equivalence by attaching the iPhone to Rose's skateboard and pushing it 1 metre in 220 milliseconds. As a result, it will register 9.8 metres per second, or the same as the acceleration due to gravity. Comparing the two screens, we can see that the red line indicates that the acceleration due to gravity is negative 9.8 metres per second, and that this is the same as the best shot at the controlled push acceleration. It's easy to see the mechanics of this with a wooden box, since we can observe the proof mass. Turning the box on its side alters the angle between the force of gravity and the proof mass. Now the proof mass is vertical. Consequently, the spring is unaffected by the force of gravity. The effect of gravity on the proof mass will be exactly the same as the effect of acceleration on the proof mass. The brass mass will behave in the same way as the skateboard accelerates at approximately 9.8 metres per second. The effect of gravity and acceleration are identical. Einstein found this coincidence highly suspicious. He decided that gravity had no alibi for posing as acceleration. He concluded instead that space is curved and that gravity is an observed artifact dependent on mass. There appears to be water on the road. It's an observed artifact dependent on refractive index. To be precise, Einstein concluded that the space-time continuum is curved by mass, and less massive objects in the proximity of a planet follow this curved path. Gravity is a dependent arising.